Question number 5, we have compound B. So component of several perfumes and flavorings. It is an alcohol, not an ester, so probably used as a solvent. It can be obtained by the hydrogenation. They use this word hydrogenation. So basically you have done hydrogenation of the benzene ring. You have done reduction of the benzene ring. So this reduction of benzene ring is actually very, very, very difficult to achieve, obviously, because you are removing or you are destroying the resonance delocalization energy. So this is a resonance delocalization or resonance stabilization energy. This is a stabilization energy. It keeps the benzene structure more stable, and that's why benzene always want to go back to the benzene structure. But this is a force catalyze. You have to catalyze this reaction, otherwise it will not happen. You also need very, very high pressure and very, very high temperature. Reagents and conditions. You need a reducing agent. Any sort of lithium aluminum hydride will not work because H minus is rich in electrons, and then the benzene is also rich in electron, very, very rich in electron. You can imagine that anything negative charge will not attack negative charge like that. So you have to do this by this hydrogenation using hydrogen gas. So hydrogen gas, that is your reagent. And then you have to use some sort of, I think nickel catalyst can do, but usually I would be thinking about platinum catalyst, where it's a better catalyst for this kind of thing. But you can use nickel catalyst, is not too bad at all. In terms of the conditions, we also need very high pressure. I don't have the exact value on top of my head, but you need high pressure to make the reaction faster as you involve a gaseous reactants that will collide more frequently at higher pressure, and also high temperature, as this reaction is not going to want to happen easily. The next thing, circle all the chiral atom in the structure of B. So I've got one chiral atom there. So this half of this top there has no OH. This bottom has OH. There's a hydrogen. There's a alkyl group there. And then I've got another chiral carbon there. There's a hydrogen. There's a OH. This side has got a branch group. This side hasn't got a branch group. So two chiral carbon there. Okay, this is not chiral as these are the same groups. And the other are all CH2. So there's no chiral center on the other carbon. How many possible optical isomers are there with from this structure B? Because you have two chiral center, you're going to get 2 to the power of 2, where you can get clockwise. Why do I talk about clockwise? Because these are what you call optical rotation of plane polarized light, as you know from the new syllabus. In fact, the old syllabus also has all of these as part of organic synthesis. The only way to differentiate optical isomers is to do with the optical activity, because they rotate plane polarized light in opposite direction. So when you draw the mirror image, they can do clockwise, they can do clockwise, anti-clockwise, and they can do anti-clockwise, which will be different because they are not symmetrical totally. And you could get anti-clockwise. So you get 2 square in terms of your probability, your possible isomers. So 4 possible optical isomers. I've just outlined the probability in terms of the combination, the possible permutations there. Now the next thing, complete the following part structure to show the structure of one of the isomers of B that will be formed during the above reaction. One of the isomers of B. So what's happening in B there? Like I said, if this is B there, so what could happen is, well, you could get OH and H. Hang on, no, I forgot something. All right, now when you add it onto the benzene ring, because this is flat, you see that thing there is, they ask for circle at B. So when I circle here, I'm not making any mistake because they only ask for circles chiral atom in there. So I circle more than one atom there because I'm not doing chiral atom for A since they only ask for B. Alright, so what I'm doing here really is just want to show that that one is flat trigonal planar. So if they are flat and trigonal planar, when you add the hydrogen for this heterogeneous catalysis, because this catalyst is in a different phase from the reactants, so what happens is the hydrogen will add onto the same phase. If the hydrogen add onto the same phase, the hydrogen and the hydrogen must be on the same side. Or you can say the hydrogen and the hydrogen can be on the same side. Alright. Even though you have 4 possible isomers, but the one that is possibly correct would have been where the hydrogen add onto the same phase, whether they are here for the 2 coming out towards you, or they are behind the screen, where the thing attacking from behind the screen, where you hydrogenate from behind the screen there. So this is okay, or the 2 hydrogen there, which means this leave the CH and then CH3 twice. So the CH carbon from 4 bond, there's 1 hydrogen there, as there's 1, 2, and 3 bond there. And then this will leave the other group being the OH there. Okay. What about this next question? Compound A can be obtained from this propan-2-al-benzene. That seems a bit funny. It's propan-2-al because this thing there, it comes from a branch 3-carbon atom. And this branch is at position 2. And in this step 2, we have a nitro group. So what has happened is you have done a substitution of this hydrogen. The type of reaction will be substitution. Type of reaction, AS introductory, organic chemistry. Terminology for mechanism, also in AS introductory, organic chemistry. Mechanism is mechanism, and then type of reaction is type of reaction. Do not get confused between the two, as introductory organic chemistry already mentioned that very, very clearly. If you want to do nitration of benzene ring, you want to introduce a nitro group, you need a concentrated HNO3, concentrated sulfuric acid, and this will create the NO2 plus mixture, NO2 plus electrophile mixture, and you will need this reflux at around 50 to 60 degrees Celsius. The next is to convert the nitro to phenylamine. This type of reaction is the reduction of the nitro group. Very, very specific there. And the reagent you would need will also be very specific in a 2-step process. It used to be only 1 step in the older syllabus, but in the 2022 syllabus, they say you must have the second one. So the first one will be you add tint and concentrated HCl, and you reflux that, and you will reduce the nitro to phenylamine. But in the presence of strong acid and concentrated, obviously, it's not going to be this, it's going to be the salt, where NH3 plus phenylamine is basic as stated in the A2 phenylamine chemistry. So to get back to the phenylamine, you must remove the excess concentrated HCl. Then you add, after that is finished, then add excess NaOH in order to neutralize the remaining con HCl and give you back the phenylamine. In step 3, we don't know what happened in step 3, but we can suggest, because from here to here, you just heat in water, so you have lost the NH2, but this NH2 must be the one that reacts. What has happened there? That must be the diazonium, because the only way you're going to lose that will be via the diazonium. The diazonium is that nitrogen with a positive charge. It's a diazonium salt. Diazonium salt. And this way, when you heat in water, the OH2 will act as a nucleophile, and then the N2 will escape as a gas. So what we're doing there must be some sort of substitution. So the type is substitution there. As for the mechanism, I don't think you need to know it as part of A-level chemistry. So suggest the structure of the intermediate cation. They are very generous. They even told you it's cation. Do not draw like the nitrogen forming 5 covalent bonds, because second period element cannot have more than 8 electrons in the outer shell, only the 2s and the 2p there. And when the nitrogen form 1, 2, 3, 4 covalent bonds, it must have a plus charge. They are not bonded together, like not covalently, but they have a strong ionic bond between oppositely charged ion there. Suggest reagents and conditions for the following steps. I did already. So step 1 was your electrophilic substitution, con sulfuric acid and con nitric acid, and reflux 50 to 60 degrees Celsius. That was it for step 1. And you should be able to write the balance equation in order to generate the electrophile. So what happened there is you will get the NO2 plus, and then the sulfuric acid is a stronger acid. When the sulfuric acid acts as an acid, you will lose H plus, so you will become HSO4 minus. And what else do you get? You get H2O, but in the presence of acid, there's actually going to form H3O plus. And by looking at these 2 plus 1 and plus 1, you get plus 2. You only have minus 1. So to balance this equation, I need 2 of that HSO4 minus. And 2 of that would mean I need 2 of that H2SO4, so that I get 2 of that conjugate base. 4 hydrogen plus 1 is 5 hydrogen. 2 hydrogen plus 3 hydrogen is 5 hydrogen. 3 oxygen, and then 8 oxygen plus 3 is 11. 8 oxygen plus 2 and plus 1 is 11. No charge and no charge, plus 1 minus 2 plus 1, overall no charge. This is the balance equation in order to show that corn nitric and corn sulfuric acid come together to give you these electrophilic species that the benzene attack and undergo electrophilic substitution to do a nitration reaction there. Step 2 is your reduction, and this was the one I mentioned. You need to now include the second step, which is aqueous sodium hydroxide, and this is essential as part of the 2022 Cambridge International Syllabus. It's stated very clearly. This is the step that's required, and it does make sense. I mean, phenylamine is basic. Even though it's weakly basic, you're going to protonate. The only way to get back the base is to add excess NaOH to remove all the acid and get back the phenylamine there. So you gotta have the 2 steps now. I'm not sure what the marking scheme for this 2015 paper actually says, but in the new syllabus, you definitely need to have the excess NaOH to neutralize the corn sulfuric acid in order to go back to the free amine, basically the free phenylamine form there. Step 4, you need to just heat it in water. What do they want? Step 3. They only want step 3, they don't want step 4. Step 3 is this making the diazonium salt from phenylamine. Classic kind of chemistry. You need NaNO2 together with dilute, or you can say HCl aqueous. That is fine, but you must keep it cold. Must be cold, 0 degrees Celsius. Usually we just say an ice bath. An ice bath will keep it at 0 degrees Celsius. You want to prevent the nitrogen gas from escaping easily until you're ready to just add water and let it warm up. Let it warm up from 0 degrees Celsius to room temperature. Then the nitrogen will leave. The water will just substitute in, and you will kick out the H plus. Combined with the Cl minus, you will get HCl. Whether produced as a solution, acidic solution, or it could even come off as a steaming white film. Although I doubt it, probably come off as an acidic solution, HCl aqueous instead. Part C, we need to suggest the structures of the organic products between each of these compounds and the following reagent. So we have product with A. So this is A, this is B. So if you have HBr, they don't mention that this is anything at all. If no reaction occurs, write no reaction. Okay, this one can react with normal alkene. What you have here is not normal alkene. What you have here is benzene, not normal alkene. Not normal alkene. So if you don't have a normal alkene, you are not going to get a reaction there. But we also know that we can do substitutions of OH with HBr there, but this is not a normal alcohol. So again, not normal alcohol. This is a phenol. So we can't replace this OH and become a halogenal alkane. So we would just say no reaction here. But now this is a normal alcohol. So the carbon with the OH, is bonded to 2 other carbons. This is what you call a secondary alcohol there. And you can do a substitution reaction to replace the OH to become Br, halogenal alkane there. You should probably be able to draw this a bit better. And then it will kick out the OH, and the H, it will kick out water. Okay, cannot use aqueous, have to be hydrogen bromide gas. And the way to produce it is usually you will generate it from corn sulfuric acid and and a bromide salt. Sodium metal. Sodium will react with phenol, so phenol does react with sodium metal, and you will get phenoxide. So what happened then is nothing. Don't know why my diagram is very ugly there. Okay, so nothing goes on with the alkyl group, but then you can get O minus and Na plus. It's always been my habit to show the ionic form. I think I did it with the rest of my tutorial as well, so you should be able to see that. So what happened now is you have O minus and Na plus. So normal alcohol of phenol chemistry, they're gonna behave the same thing with sodium. Do not forget, there are only 1 organic products even though we produce hydrogen gas, we also produce hydrogen gas because the H there, the H plus, actually comes off as H2. When you have ROH plus Na, what you're going to get is RO minus Na plus, and then you get half H2 gas. So what do you see? You see effervescence. In fact, what else do you see? You will see the sodium dissolving away into the solutions because sodium salts are soluble in water. This is sodium metal, doesn't dissolve in water. And what else can we say about this reaction? This one is sodium 0 going to sodium plus 1, hydrogen plus 1 oxidation number going to hydrogen 0. This is definitely a redox reaction there. Okay. Now I think this is the last bit of this question, this 5-mark question. So NaOH, we know that phenol is weakly acidic. Phenol is weakly acidic, so it will react with base. Normal alcohol is not acidic at all, it's not basic, so there will be no reaction whatsoever. So when I have that over here, my phenol will again form a salt, a sodium phenoxide salt. But what happened with phenol is that if I have a phenol, just phenol on its own, just general reactions, then I will get the sodium phenoxide, and then I will get H2O. So this thing is soluble, much more soluble in water. This one is not very soluble in water. So what we could say is this thing here can form hydrogen bonds, but it is not as strong as this full ion here can form ion dipole bond, because ion dipole bond as a result of hydration in your A2 energetics topic, which you can relate to there. Okay, the end of the 5-mark questions, the end of this 14-mark overall organic chemistry question there.